Hello students, let us continue with the chemical properties of ketones. Last class we have discussed with addition reactions and condensation reactions. The next set of reactions are oxidation reactions. Now mild oxidizing agents like Tollens reagent and Felling's solution, they are not reduced by ketones, but ketones can be oxidized readily by using strong oxidizing agents. As you all know, the strong oxidizing agents are either acidified potassium permanganate solution or acidified potassium dichromate solution, which generate the nascent oxygen shown in square brackets. So oxidation gives the products as carboxylic acids due to cleavage of carbon-carbon bond. And depending upon the cleavage of the carbon-carbon bond with respect to carbonyl group I have indicated here, either it can be C1-C2 bond cleavage. If C1-C2 bond cleavage takes place, then you will get the corresponding products as RCOOH and R-CH2COOH due to C1-C2 bond cleavage. In other way, if C2-C3 bond cleavage takes place from the corresponding ketone as indicated in the structure, the products obtained will have the formula RCH2COOH and R-COOH. This is due to the cleavage of C2-C3 bond. Here in particular, we need to know in detail about the oxidation of methyl ketones. A very important reaction, students. This oxidation of methyl ketones is called as haloform reaction. It is called as haloform reactions. Now here methyl ketones in particular. So what are methyl ketones? Ketones having at least one methyl group linked to the carbonyl carbon atom. So you can just look to the structure there. So this is the carbonyl carbon CH3, at least one methyl group, CH3 group is called as methyl group, should be bonded to the carbonyl carbon. Now such methyl ketones, they are oxidized by sodium hypohalite, NaOX is called as sodium hypohalite, to give the salts of corresponding sodium salts of corresponding carboxylic acids. And the methyl group will be converted to haloform CHX3, where X can be either Cl, Br or I. So just look to the reaction there. RC double bond O CH3, the entire methyl group CH3 will be forming CHX3, forming the sodium salt of corresponding carboxylic acid. Now this is a one-step equation. To explain this, I will just split that single equation into two steps. What actually happens is, there are 3 hydrogen atoms in the methyl group. So 3 molecules of sodium hypohalite, so that there will be 3 halogen atoms, will replace the 3 hydrogen here, so that it forms CX3 in place of CH3. RC double bond or CX3, and the byproduct obtained will be 3NaOH. Now this product RC double bond O CX3 in turn react with another molecule of NaOH, so that you will get CHX3 haloform and RC double bond O ONA. The product formed is sodium salt of the corresponding carboxylic acid and haloform. So this is the haloform reaction. In particular, let us look into the iodoform reaction. Yes. In case of iodoform reaction, the general representation of a methyl ketone once again is RC double bond O CH3. Now this is the methyl ketone. Now methyl ketones, when heated with iodine solution, I2 is iodine solution, and in presence of alkali like sodium hydroxide NaOH. So reaction between sodium hydroxide and iodine will form NaOI, which is called as sodium hypoiodide in the intermediate step there. But in the final equation, you will represent RC double bond OCH3 methyl ketone reacting with NaOH, sodium hydroxide and iodine. to form sodium salt of the corresponding carboxylic acid RCOONA plus CHI3, which is called as iodoform, plus 3NaI plus 3H2O, that is to balance the reaction equation. So this reaction is called as iodoform reaction. It is used as a qualitative test for methyl ketones, remember students. So this is a very important haloform reaction, in particular iodoform reaction. Now the next set of reactions are reduction reactions, the same reactions which we have looked into in aldehydes. In case of reduction reactions, the first reduction reaction is nothing but Clemenson's reduction. So when ketones are reduced with zinc amalgam, ZnHg is nothing but zinc amalgam in concentrated HCl, nascent hydrogen, hydrogen in square bracket is eliminated. So ketones on reduction with zinc amalgam and concentrated hydrochloric acid. Once again the carbonyl group is reduced to C double bond O group. I'll just show it. So C double bond O group is reduced to CH2 in the product here. R CH2 R dash plus H2O. So if you take R and R dash as methyl groups, it will be acetone or propane 2-one. So propane 2-one on reduction with ZnHg, zinc amalgam and concentrated hydrochloric acid, CO is replaced by CH2 and you get the hydrocarbon propane with the elimination of water. Similarly, if you start with the aromatic ketone acetophenone, C6H5 C double bond O CH3 on reduction with zinc amalgam and concentrated hydrochloric acid, you will end up with ethyl benzene. Carbonyl group once again is replaced here by methylene group CH2. So that you'll get the product as C6H5 CH2 CH3, which is nothing but this is the ethyl group. Ethyl group bonded to benzene ring. So it is ethyl benzene. So this is in detail regarding Clemenson's reduction. And the next reduction reaction is the named reduction, which is called as Woolf-Kirchner reduction. Now in case of Woolf-Kirchner reduction reaction, ketones are heated with hydrazine. As you all know, hydrazine is N2H4, which can also be written as NH2 single bond NH2. So general formula of ketone is RC double bond or R dash. I'll just show it once again to you all. Yes. RC double bond or R dash. Ketone reacts with NH2 single bond NH2, which is nothing but hydrazine. You will get the corresponding hydrazone due to the elimination of water R. Just look here. So from here H2 and O will be eliminated to give RCR dash. So it is not R dash being eliminated. H2 and O will be eliminated. H2 is here and yes, H2 and O is eliminated as water and you will get the corresponding hydrazone RCR dash double bond N NH2. Now this hydrazone on heating with alkali like potassium hydroxide in the presence of a high boiling solvent like ethylene glycol, the dihydric alcohol, from the corresponding hydrazone N2 is eliminated and you will get the product as RCH2 R dash plus N2, which is nothing but a hydrocarbon once again. So this is Woolf-Kirchner reduction. Now coming to one particular example of Woolf-Kirchner reduction, if you take acetone CH3 C double bond O CH3 on reaction with hydrazine NH2 single bond NH2, now there is elimination of water and you will get the corresponding hydrazone, which will be called as acetone hydrazone. And this acetone hydrazone on heating with, in the next step, acetone hydrazone on heating with the alkali potassium hydroxide in the presence of ethylene glycol high boiling solvent, you will end up with the hydrocarbon propane with the liberation of N2 gas. So this is called as Woolf-Kirchner reduction reaction. These are the two important reactions. Now coming to the last reaction, that is called as cross-aldol condensation reaction. Now this is also an interesting and an important reaction, cross-aldol condensation reaction, wherein an aromatic ketone reacts with an aromatic aldehyde. Just look to the structure there. If you so benzaldehyde is an aromatic aldehyde, functional group CHO, and aromatic ketone is acetophenone, C6H5C double bond or CH3. I have written it in the reverse form to show the elimination of O and H2 as water. So CH double bond CH. So continuation is to be shown here. So there is elimination of water, and this reaction takes place in the presence of alkali, NaOH or KOH, dilute alkali, at a temperature of around 293 Kelvin. And you will end up with the product. So the aromatic ring of benzaldehyde, CH double bond CH, C double bond O, C6H5. This part is acetophenone. This is called as benzal group. So the product formed is named as benzal acetophenone with the elimination of water. So this reaction is called as cross aldol condensation. An aromatic aldehyde like benzaldehyde reacts with an aromatic ketone like acetophenone in the presence of alkali like sodium hydroxide or potassium hydroxide at a temperature of around 293 Kelvin to give the product as benzal acetophenone. So these are the different chemical properties of ketones. Now coming to the last part of ketones, that is to know some of the uses of the first compound. It is an acetone. Acetone or propane, 2-one or 2-propanone is an important industrial solvent which is used in the manufacture of paints, varnishes and even nail polish. Another important use of acetone is for storing acetylene. I hope you all know what is acetylene. First member of alkyne. Acetylene is the common name. Ethine is the IUPAC name. Now this acetylene gas is stored under pressure using ketones. So very important use. And as you all know, oxyacetylene flame, which is used for welding purpose, requires acetylene gas. So these are the different uses of the aliphatic ketone acetone. And one very important use of the aromatic ketone acetophenone. Acetophenone is used in perfume industry because of it being an aromatic compound and having a characteristic odor. It is used in the perfume manufacturing industries. So these are the uses of ketones. So end of the topic, ketones, students. We have completed with aldehydes and ketones. Now I would like to remind you that I have been giving you all with the assignment questions as and when the topic is or concept is being completed chapter wise. Till aldehydes I have given. Now after posting the material of ketones, I will put on with the assignment questions on the topic ketones also. I request you all students to kindly write the answers to the assignment questions. Also, I hope that you are writing the material in one separate notebook and your notes are up to date, starting from haloalkanes and haloarenes up to ketones. So please revise thoroughly, students, and write the answers to the assignment questions. So next class of organic compounds is carboxylic acids, which I will discuss in the next class. I will stop here, students. Thank you.